Welcome to Ask and Learn.
In this question for part A, we're told that the X-ray provided an energy of 1,253.6 electron volts. We need to convert this to the wavelength of the X-rays used in this experiment. So in order to do so, we can use the formula energy in electron volts is equal to 1239.8 over the wavelength, and this will be in nanometers. So if we rearrange this equation, the wavelength in nanometers would be equal to 1239.8 over 1253.6, and this would yield 0.989 nanometers, and that would be the wavelength of the X-rays used in this experiment. For part B, we're asked to compare the energy of the 4f electrons in mercury and the 1s electron in hydrogen, and from these data to the first ionization energy of mercury and oxygen. So if we look at the values given, the first ionization energy for mercury, i.e. 1, is equal to 1007 kilojoules per mole. The XPS energy for the 4f electron for mercury would be 10,100 kilojoules per mole. 10 times more energy is required to remove a 4f core electron than to remove a 6s valence electron. If we look at the first ionization energy for oxygen, this would be equal to 1,314 kilojoules per mole. And the XPS energy for the 1s electron for oxygen, sorry, this not be O2, just oxygen, is 51,200 kilojoules per mole. Here we can see that 40 times more energy is required to remove a 1s core electron than a 2p valence electron. And for part C, we have to write out the ground state electron configurations for Hg2+ and O2- and indicate which are the valence electrons. So for Hg2+, its electron configuration is a core of xenon, 4f14, 5d10, and the 5d10 would be the valence electrons in the outermost shell. And for O2-, helium, 2s2, 2p6, and the 2p6 would be where we would find our valence electrons again in the outermost shell.